All right, now, so we're going to continue with parametric equations and vector valued functions. And let's do an example, call it example 1. So the equation of a helix is given by, actually, it's a vector valued function. All right, given by r of t is equal to 4 cosine t I, or let's write it this way, 4 cosine t, and then sine t, and then t over 2 pi. Or you can actually write it this way. Different ways it can come would be 4 cosine t I plus sine t j plus t over 2 pi k. Okay. So how about we try to sketch this helix for the first case. Let's sketch it for t between 0 and 2 pi. What do we get? Okay, this is going to be another challenge again for me, but I'm not going to try to draw the line. This is t, x, y, and then let's do z. Okay, so when t is 0, x is 4, y is 0, and z is 0. So I'm just plugging in t into 4 cosine t, sine t, and t over 2 pi. All right, when t is pi over 2, x is 0, y is 1, and z is 1 over 4. When t is pi, x is negative 4, y is 0, z is 1 half. When t is 3 pi over 2, x is 0, y is negative 1, z is 3/4. And when t is 2 pi, x is 4, y is 0, and z is 1. So I just went 0, pi over 2, pi, 3 pi over 2, and 2 pi. Okay, so the point x, y, z is going to be 4, 0, 0. It's going to be 0, 1, 1 over 4. It's going to be negative 4, 0, 1 half. 0, negative 1, 3/4. And then 4, 0, and 1. So our job now is to plot these points. I'm going to do as much as I can because I know it's going to give me some hard time with sketching on this iPad. All right, so I have the z-axis, and then I'm going to have the x-axis. No, I want it straighter. All right, x-axis, and then this can now be y-axis. All right, so this is y, this is x. I want up to 4 on the x-axis, so this is 1, 2, 3, 4. 1, 2, 3, 4, negative 4. And on the y-axis, I want up to 1. Oh, that is easier. I have 1 and 1, negative 1 and 1, or 1, negative 1. This is 4, negative 4. And then on the z-axis, I want up to 1, but I'm going to make my 1 a little wider. Okay, so let's plot these points. These are not going to be easy points to plot. So let's plot 4, 0, 0. 4, 0, 0 is easy to plot, that. And then we're going to plot 0, 1, 1/4. So 0, 1 is here. When x is 0 and y is 1 is there. But then we want it up 1/4. So if we move 1/4 along the z-axis, we end up there. So far, we have a trajectory, a line that's moving like this, in this direction. The next one is -4, 0, 1/2. So -4, 0 is here. You move 1/2, you'll be there. All right, so we have that. All right, still in this direction. And then we have 0, -1, 0, -1, and 0, -1, and then 3/4. Okay, 0, -1, and 3/4 is somewhere here. -1, 0, -1, and 3/4. Okay, somewhere here. All right, so you see what's going on? Ooh. Okay. So, yeah. So we're gonna go like this. All right. I'm gonna cheat a little bit. I'm gonna move this point to where I want it to be. Here. Okay. And then we have 1, we have 4, 0, and 1. 4, 0, and 1. When x is 4, y is 0, and then z is at 1. So we want something over here like that. So it's gonna be like that. Okay. So this is like a tiny part of a helix. All right. So if you have, this is the direction, that's the positive direction. It's clockwise, actually, in the xy plane. Positive direction is clockwise. Okay. Now, so remember, we're going from just 0 to 2 pi. Now, assuming we want to go from 0 to infinity, 0 to infinity, then we're just going to continue our helix. We're going to continue it this way. Okay. Oh no. We continue like this. All right. And so forth. It's just gonna keep going. So now it's beginning to look like a helix. Okay. And if we were to go from -infinity, then you know that it will also continue downwards. Keep going downwards. And so forth. All right. So that's the equation of a helix. There are some other equations that other 3D figures that we won't worry too much about. For instance, if we want the equation of a roller coaster, is actually a vector valued function that one of them is cosine t I plus sine t j plus sine t k. And I'm going to try to draw it, even though I'm not trying to be perfect with it. So if we have z-axis, then y-axis, and then x-axis. Okay, so if you have a curve, it usually goes like this, something like that. And then it might end up going back, oh no, like that, oh no. So it will come like this and then go like that. Okay. So that's what you will get if you try something, you get something like this if you try to plot this particular vector valued function. All right. So for vector valued function, just like we have derivatives for non-vector valued functions, we can find the derivatives of a vector valued function. Okay. All right, so all we're doing is just find the derivative one after the other. Okay, so if we let r of t be, say, f of t I plus g of t j plus h of t k, then the derivative r prime of t is just f prime of t I plus g prime of t j plus h prime of t k. All right, so it turns out that r prime of t is the tangent function, is the tangent vector to the parameterized curve. R of t. Okay, so assuming we have, let's say we have our z-axis, y-axis, x-axis, this is actually y, and this is x. And then we have this curve, we have a curve, a parametric curve like this, and we are concerned with a point. Say this point is t is equal to a. Okay. Then, if our vector for t is equal to a, if the vector is going, if this is r of t, then the vector for r prime of t is the tangent vector right here. It's tangent to the curve. This is r prime of t at a if you plug in a into it. Okay. All right. So r prime of t, you're going to like this. R prime of t is sometimes called the velocity vector. Why? Because if you have a curve in space that has been described as a parametric equation in the space, you can think of it, you can think of this path, this green path, as let me make it, you can think of it as the trajectory of an object in space. Let's say you have an eagle flying in space, or a fly flying. This would be the trajectory, right? So this is the position of the object, position of a bird in space, you know, at any point in time, at t equals 0, t equals 1, t equals a, and so forth. All right, so that means when you find the derivative of this position vector, then that derivative should give you the velocity. Okay, so let's try a few examples. Okay, so the first example, we have r of t is t squared 2t square root of t for t greater than or equal to 0. T goes from 0 to infinity. All right, let's find the derivative. Derivative of t is just going to be 2t, 2, and then 1 over 2 square root of t, right? And t still goes from 0 to infinity. And then we can ask ourselves, at what value is t differentiable? All right, at what values is is r differentiable? R of t differentiable. All right, so you can see that this function is only differentiable. We can only find the derivative only when we can find only for the values of t's for which we can evaluate each of the functions. This 2t, we can find the value of 2t for any t at all. Same thing with 2. But when you look at this, we can only find the value of t, or the value of this function, when the denominator is not equal to 0 or is greater than 0 actually, right? So that spoils it for the other two. It has to work for 3 of them. So it only works for the third one when t is greater than 0. So this is when the function is differentiable. Let's find the unit tangent vector for the curve r of t. Let's find the unit tangent vector. Okay. So the unit tangent vector is actually, let's call it t of t, is actually you just find the derivative and divide by the magnitude of the derivative. So you find the tangent vector and divide by the magnitude of the tangent vector. So the derivative is 2t, 2, then 1 over 2 root t. And then you have to divide it by the magnitude. The magnitude is, you find the square root of the sum of 2t squared, which is 4t, plus 2 squared, which is 4, plus 1 over 2 root t, which is 1 over 4t, right? So we're going to leave it here. No need to do a lot of simplifications. So this is our answer. All right. D part, we want to find the unit tangent vector for the curve r of t when t is equal to 1. So all you have to do is plug 1 into the answer we just got. If you plug 1 here, you get 2, 2, 1/2. This is t, not 2. 1/2. And then divided by square root of 4 plus 4 plus 1/4 um, if you simplify further, you're going to get 4 over root 33 over 4 over root 33 and then 1 over root 33. All right. All right, I'm going to describe this problem, and this is for you to solve. Number 2 or 3, I see that's 1. So let's do, okay. Let's go 2, number 2. Let's consider the motion. Consider the motion of an object in space. And this motion is given by the position vector r of t, and it's x of t, y of t, z of t, right? So its position, its x, y, and z coordinates are given by x of t, y of t, and z of t. They're given by 3 cosine t, 3 sine t, and 1. Okay. And this is for t between 0 and 2 pi. So I'm going to describe this a little bit. This is our z-axis, x-axis, and y-axis. So let's assume that we don't have z, and we just have x is 3 cosine t and y is 3 sine t. So that means we are looking at a circle of radius 3. Now that we have z is equal to 1, then that means we have a circle of radius 3 where z, the value of z, is 1. So we have this around z equals 1. So this is the trajectory of the object. It's just going around in circles around z equals 1. This is your x-axis, this is your y-axis, and this is your z-axis. And this is the trajectory of the circle and of the object, and it's in the counterclockwise direction. Now, let's look at some problems. Let's look at the first part. Let's find the velocity and speed of the object. So I'm gonna let you try this. The velocity of the object, v of t, is r prime of t. So what's r prime of t? The speed of the object is going to be the absolute value of r prime of t, the magnitude of r prime of t. Okay? Now, C, what we're going to call this A. This is just to sketch the trajectory of the object, trajectory. All right. Let's find the acceleration. Of the object. So the acceleration of the object is a of t is going to be v prime of t. Okay? A of t is going to be v prime of t. All right, so I want you guys to try this yourself. This is quite easy, maybe one of the easiest things I've asked you to try. Where do I put my try this? I want to put it up there. All right, I'm going to do it here. Number 2, and then I'm going to say, try this. Okay. What else can we do with vector valued functions? We can find arc length. We can find arc length. That is something that we can find. Okay. So we have this trajectory, right? If we want to find the length of the trajectory, how do we do that? Let's call it arc length. And then I might stop here. Okay. So if you have your trajectory, x-axis, y-axis, z-axis, and then you have a trajectory that goes from there to there, you know. Maybe an object is moving from t equals a to t equals b, right? And you're looking for the length of this trajectory, okay? The length of the trajectory now is going to be the integral from a to b of the absolute value of r prime of t. That's the absolute value of the tangent vector, then dt. Okay. So remember, we're assuming that this curve is described as r of t. The length is r of t is equal to this whole thing is just described as r of t. This, just leave it like that. It's a vector valued function. So you can think of r of t as the parameter. If r of t is the vector valued function describing this green trajectory, you can think of r prime of t as the speed along the trajectory. And then you can think of L as the distance covered from A to B, right? So L is the length of arc, right? Okay. So can we try an example? I don't know. Well, let's try one example. So we want to find the length of the arc of the circular helix with vector equation, same thing as the vector value function, r of t equals cosine t I plus sine t j plus t k from 1, 0, 0 to 1, 0, 2 pi. All right. Okay, we have some challenges here, but I'm gonna get to it. It's a very small challenge. Maybe you already noticed. So we have our helix, and the helix goes from 1, 0, 0. 1, 0, 0 is when x is 1 to 1, 0, 2 pi. 1, 0, 2 pi should be somewhere here when x is 1, but at the same time z is 2 pi. Y is still 0. So this is 1. All right, so 1, 0, 2 pi is somewhere here. So we're going to go like this. We're going to go like this. Like that. Okay. So that is our path. So this is 1, 0, 2 pi. Okay. So let us now find our r prime of t. Our r prime of t is, take the derivative of r, negative sine t plus cosine t plus 1. So the magnitude of r prime of t now is just going to be the square root of the sum of those things, sine t squared plus cosine t squared plus 1 squared. Sine t squared plus cosine t squared is equal to 1, right? So we just have the square root of 2. This gives us the square root of 2. Now, we're going to use our formula now, our length of arc formula. We're going to use this formula. So remember, we're asked for the length of arc of the circular helix. We're looking for the length of this circular helix section. So L. So let's go here, use our formula. Oh, where do I paste it? I copied it and I left it. Again, let's do this. Copy. Let's paste it here. That's good. So we're going to use this formula, length of arc. We already found our r prime to magnitude of r prime to be square root of 2. We just need to find our a and b. So t starts from t equal to 0 to t equals something, or it could be t equals negative 5 to t equals 100. We don't know. But if you look at this, if you look at where we started from 1, 0, 0 to 1, 0, 2 pi. And the equation, one of the values of the equation is just t. Z is just t. So that makes our job easy for us. That tells us that this is t equals 0 and this is t equals 2 pi. Okay? So it starts from t equals 0 to t equals 2 pi. All right? So that was the problem I was saying. That was the challenge I was saying we had. And it turns out to be easy to fix. So this is 0 to 2 pi. So I was saying it was a challenge because we're not giving the explicit values of the range of t. So we're going to go with 0 to 2 pi or square root of 2, then dt. So if you do this integration, well, you're just going to get 2 root 2 pi. So that's the length of the path. Okay. All right, I'm gonna let you try another problem. Let's call this number 2. But this is for you to try. It says an eagle rises on a helical path. So the path is like a helix given by r of t equals 250 cosine t 250 sine t and 100 t. Okay, where r is measured in feet and t in minutes. All right, now the question is this: how far does it travel in 10 minutes? Okay, t is measured in minutes. All right, so we're just going to be looking for the length of arc, and it's going to be an integral from t equals 0 to t equals 10. So I want to see your answer. What did you get? And then, all right, I think we can stop there today, and we'll start again, and we'll continue the next video, and I'll probably see you in class before then. Thank you.